Producer. John Seely Brown has developed a classic introduction style, which has become part of the conference style. I hope he doesn't think I'm committing him to futures, but I am, I hope. John is the former chief scientist at Xerox and the former head of the Palo Alto Research Center, which developed many of the tools we consider basic to our interactive communication systems. John says he's moved from chief scientist to chief of confusion, which is not an insult, it's what he prefers. John?
As usual, the existential question, just who is this guy sitting here? This actually is a non-obvious question. You have to explain that later. But let's, as usual, dig a little bit deeper. Apparently, he's a genius. How do we know this? Because he received the MacArthur Genius Award in 2011 for some pretty cool stuff that he did that you'll be hearing about a little bit later. But what else has he been up to? Well, guess what? He's an entrepreneur, a very young entrepreneur, I might add, founder of Sensi System. You hear a little bit about that, my guess, a little bit later. Also in 2005, he was awarded the top innovator of the year by the Seattle Business Journal, and that same year, the New York Times as a top technologist. Then, in 2009, he received MIT Technology Review Top 35 Young Innovators in the Country Award. And then, a few years later, 2013, he received the World Economic Forum Young Global Scientist Award. Oh yes, I almost forgot. He's a professor. Professor of Computer Science and Engineering, and also Electrical Engineering at the University of Washington. And he runs a lab that many of us know very well, the Ubicom lab at that university. But he's been helping us in more subtle ways. Here he is helping us yet again, briefing Secretary of Energy, Stephen Chu, on home energy and water sensing technologies. Water sensing technologies is not obvious. I don't know if you're going to hit that today or not. Anyways, please welcome Shwetak.
Thanks for that introduction. It's really an honor to be here. Actually, it's not easy to follow all those legends that come right before me. But I'll try my best. So what I want to talk about today is some of the work that my lab's been doing the last couple of years. And the way I want to present this work is around the techniques that we've been using to solve some of these really hard problems, which is around this concept of trying to find interesting sources of signal where presumably you might not find signal. And this is done in the context of some concrete applications that we've been interested in. And so one of the things I want to kind of share with you is the work that we've been doing on applications-driven research, in particular electricity and water monitoring in the home, and also mobile health sensing. These are really large, grand challenges that many of us are trying to tackle. And one of the challenges is how do we actually make a lot of these technologies a reality? And so I'll share with you some of the technologies that we've been working on, but also some of the concepts that we've been working on to make a lot of this stuff practical. And this notion of your signal is my noise and how to take advantage of noise as a signal will hopefully make sense as I start to talk about a lot of this. Typically, noise is something that people don't care about. They try to cancel it out, remove it. But I contend that noise can actually be a great source of interesting signal, and sometimes you might not always want to ignore it. And so that'll make more sense as I talk about some of the work that I'm doing. But before I dive into some of the technologies, I wanted to give you an overview of what my lab does. we're very much an applications-based research group. We focus on energy, health, new interaction techniques, and also low-level, low-power sensing technology. We're actually a fairly broad group. My students span electrical engineering, computer science. They build hardware, they build circuits, all the way to human-computer interaction, doing the formative work to figure out what technology we should even build for applications. So we're fairly unique in that we actually run the entire gamut of the stack, from hardware to software and everything in between. And the other thing is that we have a variety of different techniques that we leverage. We use existing infrastructures. How do we make things practical? Look for new sources of signal. Apply machine learning in new ways where we model the physics of a problem in addition to taking a data-driven approach. And also, we actually take engineering very seriously. So for a lot of you young students out there, often researchers run into this issue where their work often gets criticized for being too engineering heavy, or it's not research, it's engineering. Well, I would actually argue that engineering is actually very important to research. In fact, a lot of the stuff that I'll show you is the engineering that required to build some of the deployment studies actually opened up new research agendas that wouldn't have been possible in the past. And so engineering and research actually needs to go hand in hand. And part of that is because the engineering is required to do the deployments to see if the thing that we're even building is even useful. All right? It's not practical to assume that whatever we're doing on the research side, we can just throw over the fence and have industry adopt it. That doesn't happen anymore. That used to happen. These days, you actually have to push it far enough along that industry can actually adopt it, understand it. A lot of times, the things that we're working on are so far ahead, the industry's not even caught up to that. And so my lab does a lot of work in collaborating with industry, technology transfer, as JSB mentioned, in terms of spinning out companies, open sourcing technology, but also engaging with regulatory agencies like FCC, FDA, because the onus is really on us to educate those organizations to figure out what do they really need to think about when it comes to these new technologies of the future. So because I have limited time, I'm only going to talk about energy and health work, but I encourage you to look at our website if you're interested in some of the other technologies that we've been working on. So in the energy space, what we've been really interested in is looking at how can we provide consumers, homeowners, information about their residential energy consumption. A basic problem. How much energy are you consuming or water consuming in your home? And the question here is that there's actually a need for granular information. If you look at energy usage in the home, there's really not a lot of information about how people use energy. Where is the energy actually going? And if you think about where the big energy consumers are, a lot of people may actually say, well, why are you focusing on the home? Isn't it the large factory down the road that's the big consumer? Or if you look at this, in the United States, 1/4 of our energy use is actually in our homes. Right? So that's a significant portion. Our daily lives are contributing to that much of the electricity usage. If you look at water, it's even more interesting. More than half of our potable water usage is actually from our homes. So this doesn't include irrigation water, water for crops, and sources where you use reclamated water. This is potable, treated water that's actually used, and more than half of our water usage is in our homes. All right? So the home space is actually interesting. If you look at industries, a lot of the Energy Star mandates and Energy Star applications that they've built, they've done a good job of controlling buildings like this. But in our home, it's really actually very hard to figure out the energy usage there. And so the analogy of our energy experience right now is kind of like going to a grocery store and saying that, I'm going to go to Safeway, I'm going to buy all these products. And at the end of it, you get this nice receipt. And even Safeway does this cool thing where they break it down based on what kinds of products you've bought. So you can take a look at saying, oh, here I've spent a lot more on general goods or baked goods, this time around. But what would you say if I told you that Safeway wants to just give you this little piece of paper that says how many food units you've purchased and how much you owe? Right? You kind of complain, right? If I gave you a credit card bill that didn't give you the breakdown, or a telephone bill that didn't give you a breakdown of your usage, you might complain about where did I actually use it? Was the counting wrong? Or you might want to make a different decision on terms of your habits by looking at that. But it turns out that's exactly how your energy experience is. At the end of the month, or at the end of every 2 months, you pay that number that they show you. They might give you some esoteric numbers like kilowatt hours, CCF, gallons, but that doesn't really make any sense. The average consumer doesn't have any clue what those esoteric numbers mean. Some of these bills actually give you these charts that show you how much energy or water you've used the last month, so you can see if there's a big spike. But this is actually a real water bill one of my colleagues received at UW. This is a $3,000 water bill that he received. So instead of calling the Seattle City, they called me because apparently he wanted to use this technology in his house. And this actually ended up being a leak. And the funny thing was, when they sent him this bill, what they included in the envelope was a little dye pack to put in his toilet to see if his toilet's running. And if you think about it, if you just did the math on a 3/4-inch pipe going through the toilet and running water for a month, you still would not add up to that number, 100,000 gallons. You can't consume it. It's not physically possible. But the utility still sent him a little dye pack to see how much water he was consuming. So this just tells you that even the utilities don't have a clue on how much energy or water is being used at the endpoints, right? And so this is something that could have been rectified if we had sensing technology that could have told us how much water was being used. This actually happened to be an irrigation a leak where the leak actually happened outdoors, so that he didn't notice it. It was basically a sprinkler head that was leaking outside. So and billing happens every 60 days in Seattle. So it probably happened on day 3, and 57 days later, that's when he gets the bill. So there's really a huge lag there. And if you look at your electric bill, you still really don't have that much information about where energy is going. And if you look at the technology that's out there, right now you have a meter. It's usually this ugly thing that's strapped to the side of your house that most people don't even know how to read. Typically, this is designed for the meter reader to actually figure out how much energy you're using. You can actually read the meter, try to do the math to figure out how much energy you've consumed this week versus next week. But even the numbers are actually not easy to interpret. So this is never designed to be something that a consumer could use. In fact, the thing about a smart meter, the smart meters are making it easier for meter readers to actually read your meter. Very little of that data gets fed back. Even if it does, you're still getting aggregate numbers about how much energy you're using, not down to that level of information on exactly what appliance it might be. So if you think about, if you wanted to build a credit card receipt or a telephone receipt version of the electric bill, what would that mean? Well, one way you could solve this is you would install sensors all throughout your house. You would have a sensor in the microwave, coffee maker, bean grinder. I'm from Seattle. The refrigerator, and then all the lights. And this is just the kitchen. And this is only half the appliances in the kitchen. And if you had a sensor behind an oven, how are you going to pull that oven off the wall to install a sensor? So really, installing sensors everywhere just doesn't make sense. It's not even practical, let alone cost effective. And so our approach has been looking at trying to solve the problem of how can we get away with one sensor installed in a house that gives you a breakdown of energy and water usage down to each appliance, all right? One sensor for all your appliances, all right? So the idea here is that we can make one really intelligent device that installs somewhere in your house and then use machine learning to help break down that energy usage by using a combination of that hardware and that software to give you a credit card bill-like receipt. And so that's the work that we've been focusing on the last few years. And so there's been prior approaches. There's been people where they've taken smart meters, they look at that data coming out of it, and they can apply machine learning to say what appliances just turned on and off. So if you have an oven turn on, you see a large 10-kilowatt spike, that might be an oven. If you see a 100-watt spike, that might be a light bulb. But it turns out these days, almost every consumer electronic devices look the same. A laptop, a television, a DVD player, they're all roughly 50 to 150 watts. So if you use that technique, you can't really tease apart anything because everything looks the same. Because everything's becoming more and more efficient. At the same time, everything's also looking similar. I mean, things like an oven or a big load like that, it's easy to tease apart, but everything else is just kind of in the noise there. And so what we've been doing is looking at this from a very different perspective, is looking at what other sources of signal are out there. So if you think about what's in a consumer electronic device, like the laptop I'm in front of right now, or the projector that this thing is operating with, is that these devices have what's called switch mode power supplies. So what a switch mode power supply is essentially, it's a little piece of hardware that's in these consumer electronic devices that takes 120 volts or 240 volts or whatever, depending on what country you're in, and it brings it down to a usable 5 volts, 12 volts. And typically this used to be done with transformers or a resistor network. The problem with that is it's really inefficient. If you go from 120 volts down to 5 volts using a transformer or resistor, you dissipate the excess energy as heat. So you're just wasting that, right? Well, Energy Star now mandates that every consumer electronic device has to have a switch mode power supply in it because these are more efficient. What this does is it switches the current in and out when you need it, and it does it quickly enough that you don't see a lapse in the actual current flow. But what that means is if you're stepping down this power, you're actually doing it in a more efficient way. So you're not actually wasting it as heat. But the side effect of that is, even though it's very efficient, it's very popular, they're small, is that they produce what's called electromagnetic interference. What that means is that how many of you had this issue where you're about to get a cell phone call and then the speakers around you start buzzing, right? Well, that's EMI generated by the radio signals coupling wirelessly to the wire that's near your speaker, and it's actually conducting up to the speaker, and it's making this hissing sound. All right? That's radio waves that are actually just wirelessly coupling to that wire. So similarly here, when you have these power supplies that are switching on and off very quickly, it actually creates a magnetic interference on the power line. And often, most electrical engineers go through great lengths to build hardware to cancel that out, remove it, because it's something that is often a problem. It's something that you don't really care about. But it turns out that lots of these devices that we interact with have these. Even that little iPhone charger has a little switch mode power supply in it. And what that means is that if you take our little piece of hardware and look at the power line, you can actually see all the different appliances on the power line. So this is a spectrogram where the x-axis is frequency and the y-axis is time. Think of each line as a radio station. So each power supply is going to be resonating or has a different frequency in it, because the kind of power supply you're operating with a load is going to be different. You're not going to have the same power supply in a TV versus a compact fluorescent light bulb or an LED. So the power supplies are slightly different. And so what you can see here is you can see at any given moment at the same time, you can see here's where the CFL light bulb turned on, here's the TV turning on, here's the LCD monitor that was plugged into the house just to collect this data, and then a number of other things happening there too. This is all basically coming from the power supply that's inside the electronic device that we're looking at. And in fact, you can see this anywhere on the power line. This sensor is just plugged arbitrarily into an outlet somewhere. All right? The sensor's not behind every appliance. It's just arbitrarily plugged into an outlet somewhere. And so what we can do is we can actually take the circuit model of all the commonly occurring appliances out there and figure out what their noise signature is. So if you take a complex fluorescent light bulb, for example, so this is a rough, high-level circuit of what that is. You know, it has a bridge rectifier in it, it has a lamp in it. But if you just modeled what that would look like in terms of the noise it would put out, you can actually try to simulate that. And so what we've been doing is our hardware picks up all that signal. We've actually created these models where we can reverse engineer the appliance that's just turned on based on its noise characteristics. All right? So this light bulb has a particular characteristic. When you turn it on, it has to heat up. So there's this burst, and then it slowly heats up, and it's actually warm enough to operate. And then there's a frequency shift that happens, and all this is modeled based on the appliance itself. And so from that fingerprint, we can actually say that that was actually a complex fluorescent light bulb. Similarly, a TV has its own signature as well. So this is actually a TV. So this is actually changing in frequency over time. The reason for that is if we watch a movie, it's not just a flat image, right? If you're watching a movie, the background is changing, the backlight is actually trying to catch up, it's getting darker, lighter. And so as you're watching a movie, the power supply is trying to push more current into the TV. So as a result, the power supply is changing its frequency as it's trying to dump more current into the TV. This is actually the backlight changing of the television. A light bulb's not going to do that. A washing machine or dishwasher's power supply is not going to do that. This is very much conducive of what a television looks like. All right? And so again, from that noise source, we can actually reverse engineer that, oh, that was actually a television that was just turned on and off. And so these are this is just a handful of devices that we can detect using this technique. So different stoves, ovens, dimmers. All of these have different noise characteristics that we've learned over time. And there's many different ways to do it. There's three approaches that you can actually learn these signatures. One is you could brute force it. You could go to Best Buy at 6 a.m. in the morning, plug in all these devices, create the signature, and capture it, and then do kind of like a pattern matching technique. The other is to model it, like I talked about, where you can take the circuit and you can try to reverse engineer it. Or you can actually look at other sources that may actually have this. So FCC actually has a lot of this information already, so you can use that as a source. But the key here is that the noise source that a lot of people never really looked at is actually a really interesting signal source on energy use in your home. So we've done something really similar with water, too. So in the electricity space, you have electromagnetic interference that's all over the power line that you can tap into. But how can you do the same thing for water? How can you build a single sensor that can give you water uses on a toilet or a dishwasher or a washing machine that's far away from your sensor? And so the traditional way you could think about doing this is that you could put in a smart water meter. So if you see something consuming 5 gallons per minute versus 20 gallons per minute, that could tell you that that's a toilet versus a irrigation system. But the problem is you have to cut into the pipe. You don't really want to have consumers doing that. So what are some easy ways to install something where you can get at that information? So the way we've done it is in a slightly different way. So if you look at the plumbing system in a house, you have the cold line and the hot line. It's all actually interconnected. People often have the misconception that the cold line and the water hotline are completely separate. They're actually connected. They're actually connected by this thing called the water heater, which you can think of as a giant capacitor. You have hot water coming out, you have cold water coming in. So the hot and cold lines are all interconnected. So the entire plumbing infrastructure is this branched network of pipes. And so what we devised was a way to just tap into any location there. So in this case, it's a little pressure sensor that's on a hose spigot, all right? And what we do is we actually look at the pressure changes that happen in the plumbing infrastructure to infer what water fixture actually turned on and off. And the idea behind this is, how can we use that minute changes in water pressure to say that that was a toilet versus a dishwasher or a washing machine? And the other nice thing is that we don't actually have to cut into the pipe. This is actually at the end point. This is something where somebody can actually install. It's at the hose bib. And so what that looks like is, here's a faucet turning on and off. Here's a toilet and tub. The valving tells you a lot about what the signal is going to look like. So the electromechanical valve in a dishwasher or a washing machine is going to look different from a hand-operated sink valve or a flapper in a toilet. And so you can actually look at what that signal is going to come out as and actually figure out what that looks like and then say that, oh, that looks like the signature for a toilet or a washing machine. And because that plumbing infrastructure is all interconnected, you can install the sensor anywhere on the plumbing line. So in this case, this is an example of one that screws onto a hose bib. And so you can actually create the same kind of modeling technique that we did for the electricity space, where you can actually identify what fixture is being used, but also how many fixtures you have. If you think about where the plumbing infrastructure might be laid out, so if you have a toilet upstairs and downstairs, even though the shape of the waveform might be similar, the parameters in terms of how they decay or the amplitudes are all different. So you can say that's the upstairs one versus the downstairs one. Again, using only one sensor that's on the plumbing line. And so we've done a number of different analysis here where we had to actually bite the bullet and have to install sensors everywhere in a house. How do we actually validate that this thing actually works? So here's an example of sensors at every fixture in a home, all right, to identify, well, did that thing actually turn on, and did the algorithms and the hardware actually say that that's what's going on? So on average, the electricity technology operates within 88% for every appliance that's in there. If you do it at a category level, saying that it's lighting versus consumer electronics, or if it's heating versus air conditioning, so if you make that a 12-class problem, the accuracy actually goes up to 93%. So it actually fairly accurately can identify appliance usage down to each level. And again, for water, it's a little bit of an easier problem because there's fewer water fixtures in a home environment. And so, so the accuracy is very high in that regard as well, nearly 97%. So some of the things that we've done with this data is we've built user interfaces where this is one example of kind of an engineering interface where you have information about how much how much electricity you've consumed, how much you owe, how much you're consuming right now, but how much you've also consumed the last 7 days. But the more interesting thing is the usage details at the bottom. So this is in real time breaking down the energy usage in this particular house from that one location. So the main floor lighting, the refrigerator, the oven, the cable box, the laptop. And so this gives you the percentage that's actually at that month being contributing to your energy usage. And if you leave something on, it comes up as yellow, and if you turn something off, it actually turns off. So one of the things my wife and I do is we take a quick look at this to see if we've accidentally left something on, for example. This is what the water interface looks like. It's really similar in that how much you consume the last 7 days, but also today's water use is based on each fixture. So you can sort out the long-term debate on who takes the longest shower or uses the most water, right? You can also sort out the debate on, do you rinse first or lather, or do you run your shower all the time? So this gives you a breakdown of that information as well. So one of the things that my wife and I use this for is when we go on vacation, now we're here in Hawaii, if we see any water usage at all, we actually get an alert. Because at home, right now, because it's winter, the sprinklers aren't on, there should be no water usage at all. And so if there's any usage that is out of the ordinary, we would actually get an alert. And so there's a lot of things that you can do without having to install sensors everywhere where you can actually get some peace of mind in terms of water leaks, but also information down to each appliance. And so some of the things we've done in our deployments is that the insights are quite surprising. If I ask any one of you what your biggest consumers are, independent of the HVAC, it's actually hard to think about what the second biggest consumer is. Because at the tail, there's a lot of things that can happen there. So this was an interesting thing that I did a couple years ago. This was a photo shoot we did for the New York Times. A photographer named Peter Menzel did a shoot where he wanted to basically take a house that this technology was deployed in and wanted to take the contents of all their appliances and put them in the backyard and line them up in such a way where you had the biggest consumers in the front and the smaller consumers in the back. And so he's done other books where he's done this thing called What the World Eats, where he took the contents of people's kitchens and photographed them. So what does the contents of somebody in North Carolina look like versus Cambodia, Sri Lanka? And it's really eye-opening to see those differences. So he wanted to do the same kind of shot, but for energy usage in one individual's home. So this is them setting it up. This was probably the longest photo shoot I've ever been involved in. It took 3 days long, about 12 people to get all these appliances out of the house. Good thing they didn't do it to my house. And then set them up in the back, and then it was literally a 2-second shot. But it took forever to take the shot. So here was the final picture that appeared in the New York Times. So I'm on a cherry picker with the 2 sensors, electricity and water, and the interface in front of me, and then you have all the appliances laid out in the back. So I'll give you the first one. The biggest consumer in their house was a pool pump. Okay, so that's going to be obvious. The pool pumps run pretty much 8 to 12 hours a day. They're the biggest consumer. What do you think the second biggest consumer probably was? Furnace fan, that's a good, okay, let me give you a little bit of context. They're in San Francisco. So they don't run AC that often. But maybe the fan on the furnace, that's a good one. Lighting, water heating, they had gas water heating, but that's a good guess too. Lighting was number 2, all right? But the funny thing was, they didn't even think of lighting as number 2. Number 3 was actually the DVR. This was last on their list, all right? The TVs were 10. The kitchen appliances, the thing that they thought was their second biggest consumer was the kitchen appliances. If you took all their kitchen appliances and added them together, it was still less than 5% of their energy use, even though they thought it was their refrigerator plus their oven. These are the things that they interact with in their daily lives. These are the things that they see. The things like the DVR is out of sight, out of mind, right? You don't really know when these things are running. So they had 3 DVRs in their house, and these DVRs are often just running. Even if you hit the off button, the LED turns off, but the hard drive's still spinning because it's still trying to record your movie. Because the experience they want is they want to make sure you don't miss your movie. And so the challenge here is, well, how would you ever know that? And so the interesting thing was that the picture that JSB showed of me with Secretary Chu was me showing him his energy use from his DVR. So even Secretary Chu, Nobel laureate, Secretary of Energy, didn't know that the DVRs consume this much energy, right? And this is interesting, where for a lot of the deployments we've done, it's these subtle things that really end up becoming the big culprits. But in this case, they thought it was the kitchen appliances. So TVs was actually a big one too. They had a lot of the older generation televisions. So the other thing that we've been able to do is people have used our technology to do energy audits. So sometimes you can ask your utility to do an energy audit. Well, what do? Sometimes they come in, they say, oh, you need some insulation here and there. They may have a thermal camera to say there's some leakage here and there, but they don't really give you a breakdown of your energy use for your appliances. Well, then they can do this. So this is an example of an energy report that can be done for your house. Breaks it down to not only what category, but what rooms are in your house. All right? So this gives you a snapshot of what that looks like. The other thing we've done with this technology is, this is from ComEdison, a utility in Chicago. They've actually changed what the bill looks like. All right? So using this technology, you don't get that bill that I showed you a few minutes ago. You actually get this bill. So this shows you how much you owe, but it also shows you your top 8 consumers in your house for that month. And not only do they tell you how you've done for the last few months, but they compare you to your neighbor. So some of you may actually already get bills that compare you to your neighbor. But the problem is, what if you have, so I actually have an electric car, and so I always get compared to the wrong neighbor who doesn't have an electric car. So I'm the most inefficient person on my street, right? Because they don't have any context about what kind of energy usage you have based on your appliances. We actually compare you to the right neighbor, the kind of load profile. So this home has 2 refrigerators versus 1 refrigerator. It looks like this home may have 3 individuals versus 6 individuals. So we actually compare you to the right the comparison base. And so it tells you if this is a behavioral thing or if it's actually an appliance degradation problem. And we get this every month. And so the feedback is actually actionable. So if you were to upgrade to that energy efficient washing machine, here's what the payback would be within 6 months. So everything you get is very much tailored to you, and it's actionable. So people may not look at that iPad or iPhone interface, but you get this bill at the end of the month. You get this in the email of the bill that you're about to pay. So some people have auto pay on, so they might not actually see it, but we have as many opportunities as possible to show this to them. And so, as I mentioned before, a lot of this technology is already being deployed. And so we've commercialized it where it's been installed in homes through utilities, through consumer installs. But one of the other things we've been using this for is evaluating conservation programs. So the federal government has a mandated 10 to 15% energy reduction across the board for every state. But that's where it stops. Well, how do you do that? Well, if you're going to send out CFLs and LED bulbs, how do you know you even hit that target? Well, what they can do is use this technology to see that, okay, And in this home, the LED lighting was introduced, and you can see how much energy was saved based on that program. So this is one way to validate if a conservation program actually worked. Secondly, you can actually start to do demand response in a different way. So some of you may have heard of this demand response thing where you might install this thing on your air conditioner where if it gets really hot, a lot of load being pulled, and they might turn your AC off. That's pretty uncomfortable, and a lot of people actually opt out of it. In fact, my parents cut the wire for the demand response system years ago, all right? So what you can do now is, because we have a breakdown of your energy use, we can just let people opt in and opt out as needed. So let's say you want to opt in. Okay, you just turn your AC off at 5 p.m. like they say, and you just do that for as long as you want. And let's say you have family over and it's really uncomfortable inside and you need to have the AC on. Well, you just turn it on. We know exactly when you turned it on and off, and we know when you actually cooperated, and we just prorate it. So it doesn't have to be this binary thing. It could actually be something where consumers can actually be the controllers for their demand response system. And so in our deployments, we've been doing this for about 8 years now. We've seen across the board, without having any control system installed, this is all human behavior change of 12% reduction in energy use, just by giving people feedback, all right? And if we added the control systems on top of it, that just adds on top of that. This is just giving people insight about what their energy use is like. So I'm running out of time because we had a little bit of a late start, but I want to talk briefly about another topic, which is some of the health work that we're doing. So some of the health work is kind of similar in spirit, where what are some interesting sources of signal to solve some of these interesting health problems? So in our home health sensing work, we've been looking at how can we leverage the mobile phone for health sensing, all right? There's a unique opportunity to kind of increase the quality of care while decreasing cost. And that's kind of an odd statement, but that there's a possibility with that with the advent of the mobile phone. A lot of the things that we're looking at right now is how do you actually help people with chronic diseases manage their disease? And there's actually a unique opportunity with mobile phones. There's tons of work, and there's actually a number of amazing research projects that are being showcased here, looking at how we can use mobile technology for health. And one of the things we've been looking at is not just using the phone as a data logger, but how can you use it as a health sensor with very little modification to the phone itself. All right, that's what I want to share with you with. So this is a picture of Ted. So this was Ted met a few years ago. On the right is Regina Benjamin, who was our former Surgeon General. She's actually getting a full physical using a phone. So on the left there is actually a bunch of different companies that built phone adapters where you can put a stethoscope up to it, a blood pressure monitor up to a phone, and you can do a full physical makeup using a phone and a few sensors. But one of the things that we've been looking at is what would it mean if you could just repurpose all the sensors that are already on the phone to do the same kind of physiological sensing that you could do with some of these other iPhone attachments that people have been building. So if you look at the modern phone, there's lots of interesting sensors on there. There's the capacitive touch, accelerometer, microphone. There's the Wi-Fi signal coming off of the phone. There's speakers. But what are some clever ways that we can take advantage of these sensors in ways that people haven't really looked at before? And even future phones are going to have cameras all over them. If you look at the Fire phone, there's 4 cameras on there to get the pose and orientation of it. But the problem is you can't just put every sensor on the phone. Some people have postulated saying that you can put a heart rate monitor, a galvanic skin response sensor, all these sensors on a phone. It's all going to be on it. But the problem is you're kind of limited to what people are going to carry in your pocket or in a purse. You can't just make the phone arbitrarily big. In fact, there's actually technological limitations, too. It's not just what you can carry. If you look at the size of the phone, there's actually a limit to how small this thing can be, because if you look inside of the iPhone 5 or 6, you already have more antennas that people can imagine already in there, right? And if you just look at what's inside there, there's so many keep-out regions and so many things in there. If you add yet another sensor, it's actually going to be hard to jam that in there. You just can't have an infinite number of sensors into something that already has too many sensors. And they're already working on ways to mitigate that. So we're already defying physics with these phones. So repurposing existing sensors might be an interesting way to solve some of these interesting health problems where you don't want to have an extra gizmo or gadget installed to the phone. So that's what my group's been doing for the last few years, is looking at how can we use existing sensors for doing lung function assessment. We've actually done cardiac activity. We can actually detect blood pressure by using just the sensors on the phone without having any hardware attached to it. Jaundice detection using the camera on the phone to basically do a bilirubin assessment for newborns with jaundice. And a number of other projects. And so let me just share with you one project. So this is our lung function project that we're doing, which is basically doing spirometry. So spirometry is basically a mechanism for measuring lung function. It's really the mainstay for anybody with chronic pulmonary disease. So if you have COPD, chronic asthma, cystic fibrosis, really spirometry is the way that you diagnose and treat and manage a lot of these diseases. And self-management is actually pretty interesting, because if you have chronic asthma, for example, well, you can't really titrate your albuterol unless you go to clinic to actually do this test. So you can't really do this test at home. If you look on the left, that's what a clinical spirometer looks like. It's a fairly big device. They've actually made digital spirometers. They actually have home spirometers. These digital spirometers are about $10,000. It's not something that you can actually just bring home. Even the smaller, cheaper spirometers don't actually have the numbers that you need for a pulmonologist to make the assessment. They might give you 1 or 2 numbers, but they don't give you the full volume curve. So it doesn't quite give you the right information as the things on the left there. And so what is spirometry? You take a deep breath in, you blow into this tube as hard as possible, and you get a flow volume curve, a flow time curve. And if you just look at the curve tells you if you have obstruction, so if there's a dip, if it doesn't go to your peak volume, it means there's a restriction. So they look at the curve and the numbers to see how they're going to diagnose that particular condition. But what we've done is we've actually built an application called Spirosmart, which is actually a mobile phone spirometer. And this is completely done in software. There's not a single hardware attachment on the phone. All right? And this allows people to take this phone with them. In fact, this is their phone, and they can do this assessment daily, monthly, weekly, depending on what their regimen is. And they can do it at any moment. And they don't have to carry around a peak flow meter or another gadget. So the way Spirosmart works is you hold the phone, arms reach away, and you blow at it as hard as possible. In fact, you don't even need a mouthpiece, which is something that makes it even easier. The data is sent to the cloud, there's the machine learning algorithms, and then basically all the results come back down to the phone, goes to the personal health record, and goes to the nurse case manager, all right? And so how does this work? The way this works is that a traditional spirometer has a turbine in it. It's not that sophisticated. All it is a low turbine. The faster it spins, the more flow going through it. But in our case, we don't have a turbine. In fact, we don't have anything between the mouth and the phone. You hold the phone, arms reach away, and you blow at it. And so what we do is we actually use the human body as the sensor. So the vocal tract actually acts as our sensor. So as you're blowing out, the air coming out of the vocal tract ends up getting modulated. And this is something that we can't audibly hear, but a microphone on a mobile device can hear it. And so what we do is we actually model the vocal tract of a human to basically turn the vocal tract into a flow sensor. So in a way, we're actually more directly getting lung function flow than what a spirometer does, all right? And so if this is a 3D model of a trachea. Usually I actually carry around a 3D printout of this trachea, because it's interesting where if you were to blow into the trachea, you can actually hear the resonances. As you blow harder and softer, you can kind of hear the subtle resonances. This is what we're picking up on. As the flow slows down and increases, we can hear it on the microphone side. And so what we've done is we actually created the circuit model of what the lung function looks like. So as flow is going through, and if there's restriction or obstruction, it creates these resonances that the phone picks up, all right? And so we did a clinical trial. The medical community just didn't believe it. There's no way this is possible. So we did this clinical trial where we had people use a traditional spirometer. So this is a $10,000 clinical spirometer, and use Spirosmart, all right? So this was a counterbalance study where they used one over the other, and we counterbalanced that. And so in 147 patients, this is through 3 clinical trials, actual trials at the med school, we're actually within 5% of a clinical spirometer. So to put that into context, what that means is the American Thoracic Society says that the average error between just you doing a blow now and a blow 5 minutes later is 7%. So we're already within ATS's guideline on how much error a spirometer already has. And this is done with a phone app, all right? So this is almost as accurate as that $10,000 clinical spirometer. So the other thing we wanted to do was, okay, the numbers are great. They're very accurate. But what would a pulmonologist do with this? So we actually create the same charts that the pulmonologist would look at with their spirometer. And so what we did was we basically took the patients that they were seeing and we swapped the charts. We swapped the charts of their clinical spirometer data versus our Spirosmart data. So this was all post-analysis. So they were already diagnosed. So we weren't doing diagnosis with this. This was doing post-analysis. But they didn't know if it was a Spirosmart generated chart or if it was a clinical spirometer generated chart. And it turned out that every single diagnosis, all 147, were exactly the same. They actually didn't misdiagnose anybody, which meant that the curves that it was producing were consistent with a clinical spirometer. And so this thing is actually, so we're actually going through FDA right now. So it's going to be one of the first mobile phone apps to go through FDA that actually can do diagnosis, all right? But this is quite a challenge. When I first went to FDA, when I did the initial meeting, they said, all right, this is easy. It's a spirometer. You take this giant 3-liter syringe, push it through your mouthpiece and see what the number looks like. If it says 3 liters, then you're done. It's like, well, we don't have a mouthpiece. They're like, well, let me see your device. So I put my phone on the table. They're like, well, let me see your device. Push it a little bit closer. Well, where is your device? Push it a little bit closer, and I showed them, here's the app. You want to try your lung function? They declined. And so, so right now, it's a big challenge because if you think of the issues with what a traditional spirometer does, it's very different than a clinical spirometer because the errors that people produce are different, right? Because the error now is if you move the phone. But we know that because there's an accelerometer in the phone. There's a lot of things that they don't really understand. So that's what we're going through right now is techniques that they didn't think were possible in the past are actually completely possible now. One of the biggest issues they had was, well, what happens if you're playing Angry Birds, you pause the phone, you do your spirometry, and Angry Birds is using up too much memory. It's like, okay, well, as computer scientists, we know how to monitor the memory. We know if the memory's too low, if the performance is being degraded, we'll just lock out the phone app, all right? So that's some of the challenges that we're looking at. But in all seriousness, there are some other interesting challenges. This is a very technique-dependent test. If you're having people do this at home, they can actually just do a half blow. They can just blow at it and just stop. In clinic, you have a nurse sitting next to you saying, oh, you're not blowing hard enough. You need to go harder, faster. And so what we've done is we've looked at incentive graphics and tools and video that we can play on the device to help encourage them to do it right and do it faster. And also, if they do it incorrectly, we can teach them in real time. The other thing that we found is the mental model is completely different for physicians now. So when you see an error in a spirometry graph, they know exactly what happened. Oh, they put their tongue in the mouthpiece, and they pulled it way too fast. But when you see an error here, it's completely different, right? Because their mental model is what were trained with a traditional spirometer, not this. And so one of the things that we have to do is we have to modify the errors to look like what it looks like in a regular spirometer, which is kind of fascinating, but it's because of the training differences. And I mentioned about regulatory. So some of you may be wondering, well, what happens if you're trying to deploy this in other parts of the world? So we actually have about 1,000 patients that are using this in India. Well, not everybody might not have the same smartphone or the right smartphone. So we actually created what's called SpiroCall, which is literally a 1-800 number you dial in with any landline, and you can do the same measure. So what you do is you take any feature, you can take a feature phone, a landline, you can actually go to a phone booth, call this number, and you actually hold the handset at arm's reach away, and you blow at it, and it actually does all the processing in the cloud. So it's not as accurate as the iPhone app or the Android app, but it's good enough as a screening tool, all right? So in this picture, they're actually using a feature phone. It doesn't even have, you can't even write code for this thing these days, but you can still use it as a tool. And the key insight really came out of this resonance tracking that we're doing in the vocal tract, came out of speech recognition. There's 40, 50 years of speech recognition technology history out there. But some of the things that they were sitting on was this problem of resonance noises. So when you do speech tracking, there's this extra noise that happens, right? When you're trying to get the word the or it, there's this resonance that occurs that the microphone picks up that we can't hear. And so they tried for 50 years to figure out how to get rid of that noise. But what we did was we completely turned that problem on its head and said that, you know what, that feature tells you about the shape of your vocal tract. And that's what we were doing. And so some of the fascinating things is that we're not only cited in the medical community for this work, speech recognition researchers are using our work to improve their technology. So this is yet another example of where you can use applications-based research to drive interesting new research questions that can solve other problems that people haven't even really looked at. And so by taking this kind of unorthodox approach to this resonance tracking of the vocal tract, the speech recognition community is now using it for their own applications now, all right? So I'm going to end it there just because I want to have some time for questions. But we've done other things with cough detection. So we've been working with the Gates Foundation in terms of looking at how can we use the same techniques that we're using to detect cough, but also can we identify the cause of the cough. So can we, from the cough signature, figure out it's a TB cough versus a non-TB cough? So we've been deploying some of our microphone sensors in cough clinics all around South Africa to basically try to figure out if we can do epidemiological studies on the prevalence and the spread of tuberculosis, for example. All right. And one other quick thing I want to talk about is we've also been doing some work in sleep sensing and sleep monitoring. One of the issues with sleep sensing is typically if you have a chronic sleep ailment, you go into a sleep clinic and you have all these sensors that are put around you. There's been researchers that have tried to do sensor networks around you where you don't have to touch the body, but you have to be in this really cocoon-like position. But one of the things we've done is we've actually figured out how you can use the 2.4 gigahertz signal that's already around us from things like an access point to give you information about breathing and sleep hygiene. So in particular, if you're in this room right now, we have a bunch of wireless around us. One of the things that networking researchers are often doing is trying to figure out, well, how do we get rid of this multipath? Multipath is when a wireless signal bounces off the human or a chair or a wall, and it comes back, right? And that actually causes problem for throughput and performance. But what we've done is we've actually said that if you look at this multipath, we can actually get the minute movements of the chest in a room, for example. So we've actually looked at how to use regular 2.4 gigahertz wireless to actually get breathing rates of while people are sleeping. And we can actually do this while they're sleeping, while they're actually active on a laptop or walking around to actually get real-time breathing assessment without having to have a single sensor on board. In fact, it's using the sensor, it's using the signal that's already around us, which is basically the Wi-Fi or any other cellular 2.4 gigahertz signals that we're already being bombarded with, all right? So this is yet another example of using the noise as a signal source, all right? I'm going to skip a couple of these other slides, but I just kind of want to end it there where I think the interesting thing that we've been able to do is looking at new signal sources that weren't possible in the past, but also looking at ways that you can actually have some of these interesting engineering problems that we're solving that are coming up with new, that lead to new research questions that we can ask. Without these deployments, there's no way we could have asked some of these more fine-grained research questions later on because we wouldn't have even got to that point until we had done those deployments or done those studies, all right? So thank you, and I'll take questions. So while people get set up for questions, I want to explain this picture. So this is a picture of my students. So a lot of there's no way I could have done this without the students. The students are the ones that I just come here and speak about their work. They do all the work. So this was a couple years ago. This was in Maui. One of the things I was joking about a couple years when I first started at UW was, if I ever get tenure, I'll take everybody to Hawaii. I actually took the entire lab to Hawaii. So this is a couple years ago when I got tenure, and they were like, "Wait a minute, you're taking us to Hawaii and we don't pay for it?" Yeah. We're taking you to Hawaii. So I took all 14 students, took them to Hawaii because this is the best gift I can give them, right? Because they work so hard and they don't bat an eye, and I just owe it to the students.